Hey, my name is Lakshay, and today I'll be going over assignment 1, Fashion Mints for Applied Machine Learning. We're just importing our libraries and modules up here and loading the dataset. We just have an array for the names for the labels. Here we could see the number of dimensions and the size of the dimensions for the training images, labels, test images, labels. Here you get the length. You have the first 10 labels of it. Here you have the digital content at index 5, and here you have the image plotted out actually, so you could see it instead of that was for the neural network. This is at index 5. At you get the label number 2, which corresponds to a pullover. Here we have for test image 500 and this is test image 500 at index 500, and that label is also 2, so they're both pullovers, but you can see the difference between the pullovers. There's a big difference. Just importing keras libraries. Here we're creating our first module, neural network. We're just normalizing the image so it's a bit easier for the model, and so any certain weight doesn't bias the model a lot. We're using Relo for the 2 hidden layers, and for our last layer we're using softmax. Softmax, essentially what it does, it gives each neuron a probability to predict which label or class that image is, and it does it by giving it a raw score in logits. But what you can think about it is, it's essentially each neuron has a vote. They vote on who they think the image is going to be, like the label of the image, and the class with the most, or the label with the most votes, is the one that's picked. We're just doing a sanity check, making sure what we actually did here we did, and you can say we flattened it. We have the dense layers, 512, 512, and then the regular 10. Here we compile our model and run our model. You can see in model A we use the atom and sparse categorical cross entropy, and we ran it for 10 epochs. Second one, we first had to convert it into categorical for the test and train labels, and then we use RMS prop and categorical cross entropy. How do we compare fashion mints compared to regular mints? Well, you can see from fashion mints to regular mints, there's fluctuating on more shapes and sizes. So like, for example, a hoodie or a pullover like this, there would be multiple sizes, colors, patterns, textures that are there for just one item, and this is just for one item. There's also other labels for fashion mints, like you would have a shirt from underneath, and it would be really hard for our model to really differentiate and distinguish between like a regular t-shirt, a shirt, a hoodie, because they look very similar to the model, but to us there is a difference, and even to us sometimes it's hard to tell the difference. While on regular, like numerical mints, there's a big difference between on the numbers and the way they look. And there's also standardization between the numbers. Most people write the number 2 in the same way, and the number 3 in the same way. You could say 4, sometimes they write it like open-ended, or they cross it out with the little triangle. But there's not too much difference. In fashion mints, you have difference. You could have thousands of difference just between one hoodie to the next hoodie. And from that, we can infer that the accuracy between numerical mints and fashion mints, it's going to be off, and model's going to predict numerical mints a much higher and chance compared to fashion mints because of the complexity of the fashion items. But if we compare the two accuracies between our two models, you could see down here that they're not much difference, maybe 1% difference. And this is because they have the same architecture, where you have like 2 layers of 512, 512, 128, and then 10. The main difference is the optimizer we use. We use Atom here, and we use RMS prop here. RMS prop, essentially what it does, it adapts the learning rate. So If we're going down steep down the slope, it might take bigger steps or smaller steps, and it just adjusted accordingly. Looking back at the previous learning rates, how Adam differentiates from that is Adam does the same stuff as RMS prop, but another thing it does is it looks at the momentum it's going at. So in early training, we kind of go steeply down the slope for a gradient, and this is because in early training, the model learns very quickly, and sometimes there is bias because the model learns a bit too quickly, and Adam helps mitigate that because it learns that, oh, we're having a high momentum going down the gradient, so it corrects that learning bias, which is that occurs in early training. For the loss function, essentially there's the same mathematically under the hood. The main difference is how they take in the data. Sparse categorical cross entropy does integers, while just regular categorical cross entropy needs one hot encoding. So it would need every label to be either a 1 or 0 and predict off that. What is the last question? And then, do we have overfitting? We do have a bit of overfitting because our test accuracy is lower than our train accuracy, but it's not that much. It's only like 3% for the first option and 2% for the second option. That is the case, but there is a lot of images. There is like, I believe, 60,000. So there is a lot of images. But again, if we add up if we have the data size be bigger, it might not overfit as much due to that.